So this is now video number 2, or part number 2 of lattice enthalpy, where we're going to go over further examples. So we have got all the data here already. So stop the video and try and construct this Born Haber cycle. So let's go through the cycle. So putting it to the side, okay, we've got our line again. Okay, we start with the line at the bottom again, and we go straight for here, and we assume that's 0 essentially. Okay, and then we put on our elements. So our elements are on. The formula of magnesium chloride is MgCl2. You can see it up there. So I'm going to put an Mg and a Cl2. Okay, so that's all balanced, all nice. Think to yourself, what's the first one I do? I do atomization. I'm going to atomize the metal. Okay, endothermic, because you have to put energy in to break the metallic bonds. And then endothermic again, because the chlorine has to have its covalent bonds broken. Okay, but this time, really important, you've got 2 moles of this. Because you start off with Cl2, you've got 2 moles, which means when you do the final calculation, you've atomized 2 moles, not 1 mole, which means you need to times that number by 2. Okay, now, next one, magnesium. We are doing ionization energy and taking that up to Mg+. But this is a 2+ ion, which means we have to do ionization energy number 2. Okay, and again, notice that is bigger, okay, because you're pulling the electron away from a positive ion. So that positive ion, it has more protons than electrons, so it's pulling that electron away and it's finding it harder to, so it has to put more electrons in because the attraction is higher. Okay, so we've got this, and we've got 2 electrons out. And I'm going to show you something really, really important now, is those electrons disappearing. So I know I didn't say this particularly in the first video, so I'm going to point out now. So the next one is electron affinity. We're going to convert the 2 chlorines, okay? And we've converted the 2 chlorines, and notice the electrons have been sucked back in by the chlorine, okay? And they've disappeared, okay? So remember that. It's very, very important. The electrons get kicked out, and the electrons get sucked back in electron affinity. Now in this one, we want to work out the electron affinity of the chlorine, okay? So we want to, now really important this, the value you calculate at the end is going to be 2 times chlorine, because there's 2 moles. Electron affinity is based upon 1 mole. So it's based on 2. There, it's 4. And then the next one is lattice enthalpy, and we're given a lattice enthalpy, which is exothermic again, okay, because we're forming bonds. And then we have our formation at the bottom. Again, exothermic in this one. And we've got a nice big one. Now, let's quickly go through the arrows and show you which arrows are going in the same direction. Let's follow those arrows. Okay. Let's follow, there we go. We follow the arrows, and there we go. The white ones can get added up together to equal the orange one because it's going in a different direction. Okay, now let's move that to the side. Okay, and we make our expression. So formation is going to equal to all the others added up. Remember that too, that's atomization, chlorine. If you go down here, you can see it's chlorine 2, which means I've atomized 2 chlorines, 2 moles of chlorine. The definition is 1 mole, so I need to times the atomization by 2. Then you've got ionization energy 1, and then you've got ionization energy 2. Okay. Now, if that's the case, you've got that, and let me just check, just put something in here, just forgotten a plus, so therefore there's a plus there. Okay. Right. So we've got that plus this, okay, plus the lattice enthalpy in green, okay. And really important thing, times 2. We're doing the electron affinity by 2 times because we've got 2 chlorines. We're doing the atomization 2 times because we have 2 chlorines. We then rearrange the whole thing. So we've got to rearrange it. Remember, we're asking for the electron affinity of chlorine, which is that there. So this one here, the bottom. Okay, and we need to minus everything else away. So minus everything away from the formation. So we've minused everything away, and hopefully you can see that here. We can minus that away, and then all we do is put the numbers in. So the enthalpy, so that basically means all of that, and then we have to do a tiny thing, divide that whole by 2. Remember, this is 2 here, so we're going to divide all of that by 2 to get that. Okay. So if that's the case, we put the numbers in, a lot of numbers, okay, and we get 364.5, okay? So really, 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 really important how you actually work all this out, all right? So just going through that again, there's your really big equation. Let's get rid of that now. Okay. Okay, we're doing all this. We have to divide by 2 just to make it really clear. And then that will give you a final answer, minus 364.5. It looks incredibly complicated, but it's simple if you keep it simple in your head as in you try and go through it systematically. Okay. What I'd also recommend, as a little bit of a tip in the exam, is you don't have to write all these out. You don't get any marks for this. So sometimes I don't label these as atomization and things like that. I just label it as process 1, 2, 3, 4, 5, 6, and then I do that. Okay, it can be much quicker, but if you do that, you've got to be careful that you know what each one of these mean. Okay, but that is how you work out a slightly more complicated Born Haber cycle with magnesium chloride. So in our final example on sodium oxide, I'd like you to stop here and try yourself. You've got all the data, you've got all the equations. Okay, we're going to go through it now. So put those to the side. We're going to construct our Born Haber cycle, and we're going to do lattice enthalpy and calculate our lattice enthalpy. So we start, as ever, with our atomization. Important thing to note on the atomization is that there are 2 atoms or moles, essentially, of sodium because there are 2 inside the sodium oxide. So that means the atomization of sodium, which is this one here, has to be times by 2. Okay, really important. We'll then ionize the sodium, and again there's 2 atoms of sodium, so therefore we have to times it by 2. Here's a really important thing. I'm going to get down here because I'll be in the way otherwise. Then you have the electron affinity. First one is exothermic, so the arrow's going down, and then we go across and we can see that you've sucked in one of your electrons to make a negative ion there. Then you've got to push that electron in. You've got repulsion. So you have to put energy in, so it's going up. Okay, and then you have your gaseous ions. Gaseous ions going to 1 mole of an ionic solid is your lattice enthalpy. So this is your lattice enthalpy here. And then over here we put in our formation. So we've got our formation and everything like that. All right, now from this point, it's really important you understand which ones to add together. So again, we've got these arrows going in the same direction, so I'm going to highlight these arrows. And you see the arrows are going in the same direction. Now just follow it along the line. And it's going in the same direction until it hits there. Okay, so that means your delta HF is equal to your all of the rest, all added up. Okay, so we have saved time by writing all of this out for you. Okay, so if this is the case, you can see here that we have taken the formation, because the formation is equal to all the rest added up, and we've substituted the numbers in. Remember this 2 because there's 2 sodiums, remember this 2 because there's 2 sodiums here for the ionization enthalpy, and then we've added all the numbers in turn up to each other, all on the white arrows, all the way along. You notice here that the lattice enthalpy, which is this one here, is added as well. We then taken all of this away, which is all of these numbers here in the big brackets, away from our formation, which equals our lattice enthalpy, and it then works out to minus 2520. Simple check for you there is the fact that it has to be negative because it's a lattice enthalpy, so if you get a positive, you're wrong, okay? And if that's the case, basically just go through the calculations again. They look long, but if you do them slowly and surely, it's well worth getting all of those marks. And really important thing is, right, if you do it wrong, if you go through it and you go and you do this and you do a wrong number, you'll mess up your final calculation and lose your mark, okay? So it's well worth spending the time. Now, as I said at the start, please, I think these videos, and I would say so myself, are really, really helpful to people. So please share, and please share and subscribe. Thanks very much.